Okay, good morning, everybody. My name is Stefan Moser. I'm one of the 4 TPC co-chairs of this year's ISIT, and I'm very happy to welcome you all here in Taipei, also in my name. It is a truly extraordinary situation if at an ISIT we can welcome a Fields Medal winner. And it's even more special if the Fields Medal was awarded for the solution of a problem that is relevant for us information theorists. And today is one of these extraordinary situations. It is my privilege and honor to introduce to you Marina Viazovska. Marina was awarded this highest honor in mathematics last year for her amazing feat of solving the century-old problem of optimal sphere packing in 8 dimensions. Soon afterwards, based on her solution and in collaboration with some more mathematicians, she also solved it then for 24 dimensions. Previously, it was only known for 1, 2, and 3 dimensions, and the solution for 3 dimensions involved long computer calculations. Marina's solution, in contrast, and I cite here Professor Sarnak from Princeton University, is stunningly simple. So Marina grew up in Kiev and got her bachelor degree from the Kiev National Taras Shevchenko University. She then went to Germany, completed her master's at the Technical University in Kaiserslautern, and did her PhD in Bonn, as recent as 2013. Then she spent some time at the Humboldt University in Berlin and at Princeton University. And in 2017, she joined EPFL in Lausanne, Switzerland, and was promoted to full professor in 2018. She's chair of number theory at the Institute of Mathematics. Now, Marina has won many more awards, and I have a long list here. The problem with winning a Fields Medal is that in the light of the Fields Medal, all the other awards dim a bit. So I allow myself not to mention them now and just go on. Marina, I can only imagine how crazy your life has become in the last 1.5 years. You have reached the first high point in your career, and I believe that the sudden interest in your person must have been a bit overwhelming at times. And at the same time, your home country was attacked unprovokedly and out of nowhere from a neighboring country. And again, I imagine that you have been living in fear for your family and friends ever since. In spite of all this, you have taken this great effort, this very long trip from Switzerland to Taiwan, to come here to give us this plenary, and I would like to thank you very much for that. Ladies and gentlemen, let's give our plenary a big welcome.
So, Stefan, thank you very much for this great introduction. I'm also very happy to be here. So as I already told Stefan, I consider this as my vacation. And so today I will speak about sphere packings, so not about dimensions 8 and 24, but about much bigger dimensions. So this is a project I'm working on with my student Nihar Gargava and a postdoc in my group, Vlad Serban. And so before, let me start with an introduction. So what is the sphere packing problem? And so the sphere packing problem asks for densest configuration of non-overlapping equally sized balls in d-dimensional Euclidean space. And so this is the problem I want to speak about today. And I will not speak anything about information theory or about applications. And as a number theorist, I have a luxury of doing so. And so what we would like to find, we would like to find maximal possible density of such configuration in d-dimensional space. And then for each dimension d, we will call this best density by delta d, the sphere packing constant. And so what do we know about the sphere packing constant? So we know its exact value in a handful of dimensions. So dimension 1 is trivial. And dimension 2 is easy and was solved long time ago. Dimension 3, it was a famous Kepler's conjecture. It turned out to be extraordinarily difficult and was famously solved by Thomas Hales. And then my contribution to the field is the solution of sphere packing problem in dimension 8. And 24 in collaboration with Henry Kohn, Abhinav Kumar, Steven Miller, and Danil Radchenko. So these are all the dimensions when we know the exact value of the sphere packing constant. And so also a very natural question, probably this is the one which is interesting in information theory, is that how the sphere packing constant behaves when dimension goes to infinity. And here we know that sphere packing constant decays exponentially, and then we can ask in which rate. And so we don't know the answer to that question, but we know our upper and lower bound, and we know that a saturated packing in d-dimensional space has density at least 2 to the minus d, so exponent is at least logarithm of 2. And also somehow we know from the upper bound, this is a result due to Khabatiansky and Levenstein. We do know that we have exponential decay, but in the Khabatiansky-Levenstein bound, the constant is different. So the exponent is different. And so now, the sphere packing problem is difficult. So maybe one idea what we could do is, so instead of considering all packings, let's consider only lattice packings. So packings where the balls are located so that their centers form a lattice in d-dimensional space. And so this is how it looks in dimension 2, for example. This is a lattice in dimension 2. And so here I remind a mathematical definition of what is a lattice. But I think there is no physicists in this room, or maybe not too many, so not many people will object to this particular definition. And so now if we have a lattice, we want to choose we choose open balls so that open balls open balls with different centers would not intersect. So this is an example of such a packing associated to the lattice, which was depicted here before. And so now how can we compute the density of this packing? So here's a definition of how we compute the density of sphere packing in general. So we are taking this big ball, intersect our packing configuration with this big ball, and we compute the ratio of the volume of balls inside of big ball to the volume of big ball itself. And because lattices are such nice periodic configurations, here this formula can be simplified. So what we should do, we just have to compute the volume of our ball and divide it by the volume of the fundamental domain of our lattice. And this will give us the density of the lattice packing. And so somehow now computing the volume of balls, limiting value in this big red ball is in fact the same information over the fundamental domain. So this is the magic of symmetric configurations. Things become simpler when we assume symmetries. And so now we can also so now the question is, if we have our lattice fixed, what is the biggest ball we can fit inside? And here, of course, it's not difficult to see that we have to take our lattice, we have compute what the shortest non-zero vector in this lattice, and then the best radius we can choose, or the maximal radius we can choose, would be the shortest vector divided by 2. And so our packing density, it would be equal to this number, the ball where the volume of the ball of radius shortest zero vector divided by 2 divided by co-volume of the lattice. And so the problem of finding the densest packing becomes the problem of finding a lattice with the longest, shortest vector among lattices of given covolume, for example, covolume 1. So this is how it looks like. So this is the shortest vector, and so we choose our balls of size just the shortest vector divided by 2. And so now let's, instead of studying the packing density, we will introduce this new constant CD, and we divide and we somehow normalize it by this constant 2 to the minus d, just because 2 to the minus d, this was this, so to say, trivial density which we can get from any saturated packing. Okay. So what do we know about this constant CD, or the same, what do we know about the best density of a lattice packing? And so here the list of dimensions where the problem is completely solved is a bit longer, but you can see not by much, which is a little bit surprising. It seems that lattice packings, they're only small subset of all possible packings, and also in each dimension this becomes essentially a finite computation to consider all lattice packings. However, still it's computationally very challenging task, and so here some new dimensions where we do know the answer, in contrary to the arbitrary packing, are dimensions 4, 5, 6, and 7. And even 9 is already a very difficult computational problem. Even though algorithmically we know how to address this problem, at this point nobody have made this computation feasible. And so now, what about asymptotics? So it turns out that here for upper bound we know not much better than we know for general packing. But here we have something interesting in terms of examples. It turns out that even though arbitrary packing is more general than lattice packing, in very big dimensions it's easier for us to construct an example of good lattice packings. And even though it is, I think it's widely believed that in big dimensions, lattice packings should be worse than general packings, because it's just there are too little lattices and too many all other configurations. However, our intuition in big dimensions is so bad that having this extra structure, it's a great help. And so what are the lower bounds? So first, we somehow this trivial bound CD equals 1 is confirmed by Minkowski. So he showed that this works not only for general packings, but also for lattices. We can have lattice packings with dimensions at least 2 minus d. And then this constant was improved, and here's only part of the story behind. So Keith Ball, he showed that this constant CD it can grow linearly, and actually before the result of Ball, we also knew that there is some linear growth, but his constant was a record for quite some time. And then Stephanie Vance, in 2011, she proved a new bound, now this time not for all dimensions, but for dimensions divisible by 4. And what was interesting in her proof is not only that she improved this constant, but also that she used lattices with symmetries, and this will be the topic of my talk today. So she used the symmetry of quaternions to construct these lattices. And then the idea of Stephanie Vance was developed further by Akshay Venkatesh. And what he used cyclotomic fields, and he showed that in in the dimensions which are 2 times the Euler-Stottian function, and so this comes again as a dimension of a cyclotomic field over rational numbers. So in these dimensions, he has this bound for Cn, which is better than linear. And so in fact, it behaves something like n times log n. But in this somehow subsequence of dimensions. And so now how do these bounds compare to each other? So this is what somehow, and here which bound from the ones which I showed you, which one is the best? It really depends on which scale we are looking at the dimensions. So for small dimensions, here I just draw what the numbers that we know explicitly. And so this is the bound by Keith Ball. So this is the bound of Stefan events. And so they look linear, and bound by Stefan events is a bit better. So here we are taking logarithmic scale. And so this is a bound by Venkatesh. So we see that now, because of its number theoretic nature, it's not a line anymore, but it is this complicated set of dimensions and bounds. And so here, for example, in dimension up to 100, we don't really see the advantage of using cyclotomic fields. And so this is another type of symmetries which my PhD student have studied. So he studied lattices which have symmetries by division algebras. And so in small dimensions, this gives a set which is different from the one computed by Venkatesh. And we also get some nice points here, but let's see what if we change our scaling. So this is when we make our dimensions very big. So here we see that cyclotomic fields become really better. Here we do see this log n
Recording
advantage.
in progress.
And so this is the curve which Nihar has computed. And so here we see that at the beginning things look very promising, like we could have done something better than cyclotomic fields. However, eventually we see that cyclotomic fields win, and so asymptotically we do not get an improvement. However, we still get an improvement in dimensions which are like up to 10 to the 30, which seems like a lot of dimensions. So, and so this is the theorem which Nihar proved in his PhD thesis. And so here again, this is this result of a number theoretic nature. So just from this theorem, one still needs to run an algorithm to see in which dimensions it works, and also which lower bounds it gives. So here there is a very explicit, actually there is a description of these finite groups that can live inside of finite dimensional division algebras over Q, but it's a rather complicated formula. So even more complicated than the one we get from the cyclotomic fields. And so now let me tell you a little bit about how the okay, so here for the cyclotomic fields, we have asymptotic growth of the dimension times log dimension for this constant CD. And for Q division algebras, it's something which is somehow which cannot be better than this bound, but there are some improvements in the individual dimensions. And so now let me explain you how this probabilistic method works. So let's start with just usual lattices, first without symmetries. So what we can do, we can consider a probability space of lattices of covolume 1. And so how do we do it? Mathematically speaking, so we define it in the following way. So this probability space, it will be the group SLDR quotient by subgroup SLDZ. And on the group SLDR, we have a Haar measure. And so this Haar measure also can be defined on the quotient. And so here, what is a nice result is that the measure of the quotient is finite, so it can be renormalized so that the total measure of this space of lattices would be 1. And then we can speak about a probability space. Okay, so here's a proposition which it says us that the quotient has bounded measure. And so now what we are interested in, now I would like to introduce a random variable on this probability space. And what our random variable would be, it would be the lattice sum function. So we take, we are fixing a function and let it be a function of compact support. For example, what will be most relevant for us will be an indicator of a ball, indicator function of a ball. And so now for our random lattice, we are computing this number, which would be the sum of the values of the function over all non-zero vectors of the lattice. And so now if we think of our lattice as being random, then this function, it becomes a random variable. And so what we might be interested in is in computing the expected value of this random variable. And so here's a small numerical experiment. So now we are choosing lattice in random, and we compute the value of this lattice sum function for the ball indicator function. So here we see that this lattice intersects with the ball only at the origin, and therefore the value of our lattice sum function is 0, and it's 0 here, and in this case. And okay, so here we are computing. So in this case, we still have 0. And as we run more and more experiments, so if we run like for 500 experiments, then we would get this number, which is somehow close to the integral to the total volume of our ball, or to the integral of our function f over the Euclidean space. And so now what we have done, we have experimentally confirmed the following theorem of Siegel, which tells us that the expectation of the lattice sum function equals to the integral of our function small f over Euclidean space. And so now we are going to use this fact for the packing problem. So as we know that for any function lambda, for any lattice lambda, and for a function f, which is an indicator function, so then lattice sum can take only even integer, only even positive values. And so this happens because every lattice, it has symmetry around 0. So if it contains some point v, then it also contains, if ball contains point v, it also contains point minus v, which also belongs to the lattice. And so now what we are doing, we are taking a ball of a volume which is slightly smaller than 2, which is 2 minus epsilon. And then we know that the Siegel's mean value theorem would tell us that the expectation of this of the lattice sum function would be 2 minus epsilon. And so we know that there exists, from this we know that there exists a lattice, so that the value of lattice sum on that lattice would be smaller than 2 minus epsilon. But if it's small, if it is smaller than 2 minus epsilon, then it has to be 0. And then it means that this function, that this lattice gives us a packing of covolume 1. And so this way we have proven that the constant CD is at least 2 for all dimensions D. And so now So now the result of Venkatesh, it actually uses the same idea, only now he, instead of considering the space of all lattices, he considers the space of lattices with symmetries. And so now let me show you how the bound of Venkatesh works. So now we consider a different space YD, which would be the space of lattices with a symmetry induced by a cyclotomic field. And so this is exactly how he does it. So we still have to construct this space. And so this is how Venkatesh constructs the space. And now each lattice in this space is invariant under the cyclic group action of the roots of unity. And now if f is an indicator function of a ball, then we know that its intersection with any such a lattice with a symmetry, it can take values which are multiples of n because of the symmetry that we have. And so now also what Venkatesh does, he proves that the analog of Ziegel mean value theorem also holds for this newly constructed space. Yeah, so we can use the same argument as before and prove that there exists so if we choose a ball which has volume n minus epsilon, then we can find some lattice in this space YD, which such that the value of lattice sum function on this ball is smaller than n minus epsilon. If it's smaller than n minus epsilon, then it has to be 0. And so we get the desired conclusion. And so now the last step which remains to do is to analyze how the totient Euler function, how it can to find such n such that the value of totient Euler function is as small as possible while n being fixed. And this happens in the case when n is a highly factorable number. And well, the best what we can do is when if we denote this number as d, then n would be d times log d. And so now I ran out of beautiful slides made by Nihar, and these are ugly slides made by me. And so another interesting question, and it's also so to study, till now we have studied the expectation of this lattice sum function for the indicator of a ball. And another interesting thing we might study are the moments. And so this is a result of Roger from 1950s. And so what he discovered is that the number of points of a random lattice of unit covolume inside of actually a centrally symmetric body, for example, for us maybe the most interesting case would be when the centrally symmetric body is a ball. It essentially has a Poisson distribution. And so here is a more precise statement. So he was able to, if he took a lattice of rank T, and then he computed the moments for this number of lattice points inside of a body S, and so the moment should be, roughly speaking, the square root of the rank. If the number of points is, roughly speaking, the square root of the rank, then one can estimate this moment, and it essentially coincides with the nth moment of the Poisson distribution up to this error term. And error term decays exponentially fast as the rank increases. And so this is a Wikipedia picture for what Poisson distribution means. And how Poisson distribution means that our points are essentially very random. So we don't have any particular structure. And so now the project we were working together with Nihar and Vlad is we are trying to reproduce this the result or to see when this the result of Rogers can be introduced, as we are working with with this lattices with symmetries. And so here again we look at the lattices which have some symmetry coming from a number field. And as I showed you before, this could be a cyclotomic field, or this could be another number field. So we take a number field k of fixed degree, and we construct a space of lattices with the action of the ring of integers of k. And then we say the first results we prove that if we now take many copies of such a lattice, then the behavior of the moments for the number of lattice points inside of the ball, we will also have this Poisson distribution. The only difference here is that, okay, so here the parameter would be different, and we would have to divide the volume of our ball by the number of finite units in our field. So in the case of cyclotomic fields, we divide by the number of cyclotomic units, or so also if our field K, if it has some finite units, then the number of lattice points inside of each ball, it will be always the multiple of this of the number of those units. And so here also we would have an exponential decay. And so, however, what was somehow also the next question we would like to ask is that, okay, so how does this constant ck, how does it depend on our field k? So now if you don't want to take more copies of our field, but instead we want to take a few copies of a field, and then to change the field, to take fields of bigger and bigger degrees, would we still have something close to the Poisson distribution? Or would this constant explode and ruin everything for us? And so here it turns out that the answer actually will depend on the properties of our field in question. And so it turns out that cyclotomic fields, they are very, very nice fields from this point of view, and that for cyclotomic fields, actually we would have a bound like this. So here we would have an exponential decay not only in terms of the number of copies we take, but also in terms of a degree of our field. And so this is still work in progress, but I hope that the result is correct and that we will be able to post the preprint soon. So, and then so now what properties of the fields are important for us? And it turns out that an important property is the Mallar measure of the field, or how small can the Weil height of elements in the field be. And so here we will let, again, k, so for an algebraic number alpha in some field k, we will consider the following two numbers. So one of them is its Muller measure, which would be the product of all places of our field. And then we take a maximum of 1 and the evaluation of an element in this field. Or another also useful parameter would be such a product which is taken only over infinite places, which are embeddings of our field into complex numbers. And so to look at all embeddings of our field into complex numbers, and then we take a product of a maximum of 1 and absolute value of the embedding of our algebraic number. And so if alpha is an algebraic integer, then these two numbers will coincide. And if it's not an algebraic integer, then they will be different essentially by the denominator of alpha. And so also an important parameter for us would be then absolute Muller measure of an algebraic integer. And so here it would be normalized by the degree of our number. And so Muller's, so the famous Lemmer's conjecture asks whether this number is bounded. So if you take this normalized absolute Muller measure of alpha multiplied by the degree of alpha, and the question is whether this is bounded for all algebraic numbers. And so now we would like actually consider fields with a stronger property. So fields where not only this quantity is bounded, but also this number itself is bounded from below. And it turns out that, despite the Lemmer's problem is still open, we have fields where this stronger property is true. And so we will consider, it will be interesting, we will consider fields with the following property, so that their Weil height is bounded from below, and their Muller measure of all elements in this field is also bounded from below. And it turns out that there exist fields where these two properties are satisfied. And so here's one is the theorem of Schnitzel, which tells us that this is true for algebraic numbers which are contained in totally real fields. If alpha is not a root of unity, it has an infinite multiplicative order. So if it's not a root of unity, then it satisfies this condition. And also we know that this bound holds for all abelian extensions of Q. And so when we are considering these nice properties with bounded absolute Weil height, then we can prove this theorem where we know that the moments have almost Poisson distribution, and the deviation from Poisson distribution is some error which decays fast in both T and D. And so another interesting fact that we found that this Poisson distribution is not always true. So that somehow we have nice fields that satisfy the Bogomolov property, but we also have fields which are quite far away from satisfying that property. And there are cases where we do not hope for Poisson distribution. And so, for example, we can take field generated by, for example, we have this sequence of algebraic numbers which have this Euler measure bounded from below, and in this case we can estimate the second moment also from below, and we could see that the second moment is bigger than what it is supposed to be for the Poisson distribution, and it is bigger by a constant. So, okay, so I think this is all I wanted to tell you. So maybe now I can answer your questions.
Questions?
I'm a little bit shy to ask this question, but I'll ask it anyway. When we use lattices in communications, we can get a really good prediction of the performance of the lattice using the minimum distance and the kissing number. So this is through the union bound. So do your results or your work on the number of non-zero lattice points, can I use that to get an estimate of the kissing number or say something about the kissing number as n gets bigger?
So, but I think if you take a very generic lattice, then probably kissing number and it would be something, I don't know. So sorry, so you mean like when you say kissing number, you mean kissing number for a particular lattice or kissing number in that dimension?
Any of the above, either a bound or something comparable to the ideas in the sphere packing.
Yes, so I would think that probably if a random lattice, it would have probably only like 2 lattices of given length, right? So, but then still, so to having something non-trivial would be like probability 0 event. Yeah, so I don't know. So and also these probabilistic results, I don't think they. Okay, as I also said, for kissing number, it's a difficulty to estimate it from above. So I don't know. I don't think that these results would be very useful in that, even though I might be missing something. So I know that constructing lattices with big kissing number, it was a big open problem where there wasn't progress recently, but also the methods seem to be very different from this. They are much more deterministic.
Okay, great. Thank you.
Yeah, in information theory, it's classical that by lattice coding you can approach what is known the capacity of the Gaussian channel. That's classical results that dates decades ago. Could you do more with this kind of results, meaning not just achieve at the limit of the rate, half log 1 plus SNR, but maybe higher moments, even error exponents, with the additional results that you have presented? Because lattice coding is classics in information theory.
Yes, so we are focusing on a packing problem, which is somehow different from capacity. And also, actually, I don't know whether symmetries do something better, for example, for Gaussian energy of a lattice. So here I don't know. So this is something we still have to do.
Hello. Here. Hello.
Yes?
Hi. Just a question about the Mahler. It looked to me like a product distance that we are using in some algebraic lattice constructions in wireless communications. Is it like the product of the components of the lattice vectors?
Yeah, so it's probably
Maybe in a different language, but
okay, but here maybe an important thing is that it's with also taking a maximum between 1 and so it's okay. So I think the
you remove the zeros, I think.
no, we are not only removing the zeros because here it's so our vector it's embedded into it has different embeddings and one can see it as different subcomponents of our vector, and then we are computing the lenses of those, and we choose only those lenses which are bigger than 1 and multiply those lenses which are bigger than 1. But I don't know, it seems like a very natural thing. It's probably also used somewhere in
Thank you.
another field. Yeah.
Any more questions? Okay, in this case, let's thank our speaker again.